Welcome to the second video relating to the alveolar gas equation, and this video focuses on its application. And in the last video we derived this equation and we said that the partial pressure of oxygen within the alveoli, which is an important driving factor of diffusion of oxygen from the alveolar gas into pulmonary capillaries, we discussed that was very hard to measure or not measurable. So what we needed to do was equate it to some other variables that we could measure. And through the derivation in the last video, we saw that this was equated to the fraction of inspired oxygen multiplied by the difference in atmospheric pressure and the saturated vapour pressure of water at 37 degrees, minus the arterial tension of CO2 divided by the respiratory quotient. And the respiratory quotient again was discussed in the last video, so if you're unsure of that, just go back and recap. And the equation really tells us that the partial pressure of oxygen within the alveoli is only dependent on four different variables. One of them is the fraction of inspired oxygen. One of them is the atmospheric pressure, or the pressure of gas surrounding the patient in question. The saturated vapour pressure of water at 37 degrees is a constant, so that doesn't count as a variable. The arterial partial pressure of CO2, which can be affected by changes in alveolar ventilation, as we're going to discuss, and in a slightly more smaller print way, the respiratory quotient, which won't change acutely, and so that's really just kind of put in brackets there for completion. So let's look at a real-world example and put some numbers in. And we'll start with normal. So we've got the alveolar gas equation here. So our first normal example is a patient called Bob. And the assumptions made about Bob are that he has healthy lungs, he's at sea level, he's breathing air, he has a normal Western diet, and he's at rest. And so now, with those assumptions, we can see how we can plug some values into these figures here and start to generate a number for the alveolar partial pressure of oxygen. So the FiO2 can be assumed to be 0.21, given that he's breathing air. The atmospheric pressure at sea level is 101 kilopascals. The partial pressure, the saturated vapour pressure of water vapour at 37 degrees is 6.3 kilopascals. A normal value for an arterial CO2 tension at rest is around about 5.3. You will see some slight differences in books, but anywhere between kind of 5 and 5.5 is reasonable. And given that he's having a normal Western diet, we can assume that the respiratory quotient is 0.8 or thereabouts. And if we plug those numbers into the equation, we end up with this equation here. And just simply calculating using those figures, we generate a alveolar oxygen partial pressure of 13.3 kilopascals. So a number around about 13 is completely normal for someone at sea level, healthy lungs, breathing room air. And in the next example, we'll look at the effect of changing FiO2. And again, here's the alveolar gas equation. Now, we've still got Bob, but this time, Bob is in a position where we can affect the FiO2 that he is breathing. So we've got a dial here, and we can have low FiO2 or high FiO2. Now, let's see what that does in terms of the alveolar gas equation. So we'll start with a hypoxic mixture, which is any gas mixture that has an FiO2 of less than 0.21. So for argument's sake, let's say we have an FiO2 of 0.15. We plug these numbers in, and assuming that all other variables remain the same, that gives us a PaO2 of 7.6, which is almost certainly going to lead to hypoxemia. I say we assume all the other things the same, in that the PaCO2 could change to help to compensate for this. We'll talk about this later, but for the sake of keeping things straightforward for this example, we'll just say that the FiO2 would be 7.6. So that's down from about 13, with just a reduction from 21% to 15% oxygen. Then we change the settings to give us supplementary oxygen. And let's say we set the FiO2 to 0.5, so 50% oxygen now. We put those numbers in, so put 0.5 in to assume everything else remains the same. And now we get a PaO2 of 40.7. So just from these examples, you can see how FiO2 has a significant impact on the alveolar partial pressure of oxygen. In our third example, we look at the effect of altitude. And again, here's the alveolar gas equation on the right. And this time, Bob has climbed up a mountain. The mountain is 18,000 feet tall, or 5,500 metres. The reason I've chosen these numbers is because there is an inverse relationship between altitude and atmospheric pressure. Namely, as we increase altitude, we reduce our atmospheric pressure. And around about 8,000 foot, or 5,500 metres, atmospheric pressure roughly halves compared to that at sea level. As a consequence, we can say that atmospheric pressure for Bob is roughly now 50 kilopascals compared to 101 kilopascals at sea level. All the other variables remain the same, and it's important to note that FiO2 has not changed. He's not suddenly breathing a hypoxic mixture, it's still 0.21. The fraction of oxygen hasn't changed, but what has changed are the number of oxygen molecules because the overall number of gas molecules has reduced. If we plug this in to our equation, we calculate that the PaO2 for Bob is now 2.5 kilopascals, which is clearly going to result in profound hypoxemia. So altitude itself, even with no change in FiO2, will result in a reduced alveolar partial pressure of oxygen. In example 4, we look at the effects that changing arterial CO2 partial pressure has. And in order to do that, we need to revisit the alveolar ventilation equation, which was mentioned in the last video. And this tells us that the arterial CO2 tension is directly proportional to the rate of CO2 production by the body, but inversely proportional to the alveolar minute ventilation. If we were to plot a graph of alveolar minute ventilation against PaCO2, it would demonstrate the inverse relationship discussed. And if we take that back to our previous examples, again, looking at the what that means for our alveolar gas equation, and we go back to Bob at sea level, but this time Bob is hyperventilating, so he significantly increased his alveolar minute ventilation, and as such has reduced his PaCO2. Let's say he's reduced it down now to 3 kilopascals. What does that mean for his partial pressure of oxygen within the alveoli? Well, if we plug that number in, we end up with a calculation that the PaO2 is now 16.1 kilopascals, which is up from just over 13 when he had a normal alveolar ventilation and a PaCO2 of 5.3. And the same argument can be made to also explain how Bob at altitude in his hypoxic state could partially compensate for that. So our numbers were as follows, where he's got remains his FiO2 of 0.21, atmospheric pressure had reduced due to the effects of altitude, and this time Bob has increased his alveolar minute ventilation such that his PaCO2 has been driven down to 3. If we plug those numbers in now, we see his alveolar partial pressure of oxygen has shifted up to 5.4 kilopascals from around 2.5, and thus this has resulted in some compensation for the effects of altitude. And climbers at altitude do increase their minute ventilation and therefore their alveolar minute ventilation and run a respiratory alkalosis. It's worth noting, however, that this compensatory mechanism can only go so far, and if you were to plot minute ventilation against PaO2, you'd see a graph that looks like this. So it's law of diminishing returns. So if you start off with a relatively normal alveolar minute ventilation and increase, you will increase your PaO2, but above roughly 10 litres a minute, the graph pretty much plateaus and there's no further benefit. So if Bob remained hypoxic at this point, despite a huge increase in his alveolar minute ventilation, the only thing that he could do in order to push up his PaO2 and improve his oxygenation would be to either increase his FiO2 by taking supplementary oxygen, which mountaineers do, or to climb down the mountain, reduce his altitude, and therefore increase his atmospheric pressure. Thanks for listening. I hope that's been helpful.